Hello, everyone. Welcome to the Friday seminar. Today, we are very happy to have Ryohei telling us about automorphism of game theory and
Okay, yeah, thanks for the introduction. So, yeah, I'll be moving at the end of March to Tokyo, and the first comment is that there are a lot of some machines I have to lease or just give. So, if myself a rice cooker or air fryers, and if you want, just feel free to let me. So, today's talk was about some logical operation of the Clifford, logical operations of the stabilizer course. And I think I have given this type of logical operators talk in numerous places. So first half of talk, you might have listened some places. But then the last half of the talk, I'll give you some recent update about the understanding of the logical operations in the non-Pauli stabilizer in particular. So let me just start with some brief introduction to the stabilizer code. So I'm interested in some stabilizer code or stabilizer models. The definition is very simple. Like you have just some bunch of unitary operators in the qubit systems. So I'm interested in some local qubit systems. Or we could have a adjective, which is a local stabilizer. And we have some bunch of the unitary operators, and we want to specify some logical qubit on which we do some quantum computation, which is simply is characterized by some span of the states which satisfy which is the ith state of the stabilizers. So that's basically it. So in many cases, people are interested in some particular class of the stabilizer code called Pauli stabilizer codes. In this case, each these stabilizers are Pauli operators. So that's this case is there are many well-known examples of the Pauli stabilizers. For instance, the most well-known example is a Pauli called sqrt, which is just given by these guys. Sqrt. These guys commute with each other, and this common eigenstate corresponds to some stores some logical qubit on torus. Okay. And the other well-known example is so-called surface form. Look like this. So it's defined on a square with boundary conditions. So on the boundary, we have this smooth boundary. We also define of the location of the stabilizers only on this rough boundary. So that this is, and this is called a surface code, and then this guy stores a single logical qubit. This is an example of the Pauli stabilizer models. And then in these setups, in these Pauli stabilizers, these stabilizers have to commute with each other in order to find a solution of the stabilizer constraint. But later on this talk, I've generalized these Pauli stabilizers to non-Pauli stabilizers. For instance, each S is a Clifford operators. In this case, we don't necessarily have to impose a combination of these local stabilizers as long as we find solutions. Okay, so this is my setup. So I'm interested in for given some stabilizer code, we typically want to do the quantum computation on the stabilizer code. So in order to do the quantum computation, we need some operations, some unitary operation which acts on these code spaces. And this is called logical operators. Logical operator is just simply some unitary operator acting on the qubit systems, which acts within the code qubit space. So, which just preserves the code qubit space. And so it's sometimes very convenient to think about this logical operator in terms of a symmetry. Like for instance, in the case of toric code, like one can regard a toric code model in terms of the Hamiltonian model, where each Hamiltonian becomes stabilizers, and then the coherent space becomes its ground state. And then like this is a unitary operator which preserves the ground state. So therefore, it can be understood in terms of emergent symmetry, which preserves the ground state. So like sometimes the perspective regarding this logical operator as a symmetry is very helpful. And in particular, recently there's an active development of the understanding of generalized symmetry, and you can use some insight of the generalized symmetry to find the new logical operations, or like study its structure of the logical operators, some stabilizer codes. Okay, so there's some slogan of the logical operator. It goes to emergent symmetries. Yeah, I bring up this kind of slogan sometimes. Okay. And in particular, sorry, is this question?
Yeah, not every logical operator. Would that right?
Why do you say that?
If you just act on a ground state, the logical operator, but you mix excited states.
Oh, so that's why I'm saying emergent symmetry. So my definition of emergent symmetry is some unitary operator which acts within the low energy Hilbert space. So this is a symmetry of the low energy Hilbert space, so therefore it is emergent. So I agree it's not exact symmetry in the sense that it doesn't have to commute with the H Hamiltonian. Yes, that's what question. Is there other question? Okay. So among these symmetry operations, particularly important class of the symmetry logical operators, so-called the transversal logical. Okay. Which is basically based on this slogan, it is equivalent to internal symmetry. And so in the sense that this transversal logical gate is some operation, unitary operations, which like is internal, which preserves the locality of the operators. So this is a particularly important meaning, because if the unitary operator is a transversal, it doesn't spread errors. So if you have some local error in some toric code models, even if you acted the transversal logical operation during the computations, the error doesn't spread. And in this sense, the transversal logical operators have some property of fault tolerance, so it has some particular.
It has to be strictly.
Yeah, so like originally, quantum information people means some on-site operators. Like so, typically in the older context, in particular, transversal logical operators mean some like unitary operators are generated by some like on-site operators U, but it is a bit too strong conditions. Like so like well, more generally, like we can kind of allow the definition of transversal logical operator to include a finite circuit. As in circuits. So like this is well, not as good as like on-site operators, but it has also preserved locality and can be easily implemented. So like in the recent context, the transversal logical operations can include some finite circuit. Sometimes people call the finite circuit as a nearly transversal logical operation. And for the people working on the symmetry on lattice, let me just comment that the internal symmetry can include a generic quantum cellular automata. So locality preserving symmetry can be generated by the quantum cellular automata, as that is defined as just a local symmetry operator which is referred to locality. But in my talk, I just focus on the finite circuit because it can be easily implemented by some acting local operation states.
So do you define transversal logical gates by the right-hand side, or do you have an independent definition? Or
well, like let's say transversal logical gate is defined as a finite circuit which preserves a pulse.
Okay, so for your target,
yeah, that's the definition I talk. So right? So, so it is sometimes convenient to organize the action of the logical gates on the code space in terms of some particular structure called the Clifford-Hierarchy.
Right, just to make sure.
Oh, yeah.
And the ENM exchange symmetry of Tori code is not transversal.
It's transversal because it can be implemented in terms of finite circuit. Like
as order 4, not order
yeah, it's order 4.
Okay,
But
order 2.
it's exact order 4 symmetry, but on the code states as the emergent symmetry acts order 2. Yeah. At least on the oriented spacetime. On the unoriented manifold, it can act order 4. So this is some structure convenient to define some action of the logical operators on the code states. So let me define it. So this is some hierarchical structure for the some subset of the unitary operators. So like if you have this kind of inclusion structures. So I define some sequence of the set of the unitary. This. So like all of them is included in the unitary group of the qubit systems. Okay, so the first hierarchy is first hierarchy logical operator is just a Pauli group. So therefore, so this can be just defined as a group generated by the on-site Pauli operators. Defined as on-site Pauli operators. So it contains a 1 or I or X. Yeah, so it can be generated by the on-site Pauli operators. That's a Pauli group. So this is a first hierarchy, the default hierarchy. And the second hierarchy is a Clifford group. C5, so like Cn, n is the number of the physical units, number of sites. And so this can be defined as some operators, unitary operators, which maps the Pauli operator to Pauli operators. So like for any Pauli operators, you take a commutator between the this operator, any Pauli operator, you get this is again included in Pauli. Yeah. Okay. So this can include also this again generates a group, and this can include, for instance, control Z or S. Basically on site where the which is diagonal to the one line. And they also see this these guys are included in this.
Is that a complete set for 2 qubit systems?
Yeah, I think so. Like this generates a like a complete set of the Clifford operators in 2 qubit systems.
Well, some comment, dagger is probably not necessary in that form. Right?
Well, conjugation of the S is not conjugation. No S is not S, so like not all the Clifford operators is not Oh, that's right. Yeah. That's correct. Yeah. Well,
Even not P, right? You don't have to.
sorry, what do you mean? Sorry, what's the comment?
When you just remove that P. If you remove that P, nothing changes.
Yeah, it's fine. Yeah, you could just eliminate this Pauli operators, but for later convenience, I'm including this. Yeah. later on, I want to group some bounds on the logical operations of the. In this case, this definition is a bit more obvious, but I agree with all topic.
Could I clarify about the Clifford-Hierarchy 1? This is the actual Pauli group, or this is a group of unitary operators which map one Pauli operator to another Pauli?
Well, this is really a sorry, wow.
There's this group people call local Clifford group, which acts on just on one side and maps XYZ into themselves.
Oh well, this is like a full Clifford group, like a which acts on the n cubic systems Pauli operators to like a map to themselves.
I'm just trying to understand this Clifford hierarchy 1.
Clifford hierarchy 1 is just a Pauli groups. Like it's just a well, this is you can understand this as like a group generated by X and Z on the on site.
Will you give some intuition why these groups are chosen as a hierarchy or a subset of each other? Or what is the intuition behind choosing these groups?
Well, what kind of intuition do you want? Like this is just well, later on I'll try to like so one motivation to define the Clifford hierarchy is that it's easy to kind of characterize the necessary condition for universal gate set. So like so within these Clifford groups, you can never do the universal quantum computation with the Clifford gates, and we always need some like higher hierarchy of non-Clifford gates in order to do the universal quantum computation. So like within these two hierarchy, you can never do the universality. You can never achieve universality. And the other comment is that later I defined some bounds on the logical operators based on some dimensionality of the operators in the local parameter code. In this case, this kind of the hierarchical structure, definition of this kind of hierarchical structure becomes immensely helpful. So like maybe you will see the motivation of this groups later.
CH3 is defined similarly.
It's just defined inductively. So like let me just define the definition of K. And let me see. So it's just operators and they follow any B is CH K minus 1.
Oh, so P is not in CHK minus 1. It's probably.
Well, it's an inclusion structure, so like a P is also included in the CHK minus 1. So this is an inclusion, some family of the. So like in particular, in any group of hierarchy, yeah.
But if it's an H,
yeah, you can just eliminate this. Yeah, it's fine. But
no, but if P is an H K minus 1, it's not going to be in, again an HK in place. That's the
sorry, what's your comments?
Does CH3 preserve Clifford group?
Yes.
By conjugation?
Oh,
Just
just a Pauli, just a Pauli, just Pauli.
Pauli to Clifford.
Just Pauli to Clifford, yes. Like for instance, a third hierarchy, well, it's just defined by the action of the Pauli operators. So it could map the Pauli operators Clifford hierarchy, but we are not sure like how this guy CH3 maps the Clifford operators. I guess it's not closed. Yeah. Clifford operator is not closed under the action of the Clifford hierarchy, I think.
The idea is that this deconjugation takes you.
If you say?
Out of Clifford Pauli.
Oh, yeah, sure. All right. And so, like for instance, class 3. So this start to contain the so-called non-Clifford gate. And this is as I'm motivated a bit earlier, this turns out to be very important when we define the universal gate set. In particular, we always need at least single non-Clifford gate to define to get the universal gate set. Yeah, and also it is known that while the Clifford gate set cannot do the universal computation and actually can be efficiently simulated by classical computer, but if you add a single non-Clifford gate set gate in addition to the full Clifford gate set, it is always universal. So like the genuine element of this CH3 becomes very important. And now I want to define some bounds. So on the possible logical operations on the local topological parallel course, there are actually adjectives I want to define. So Bravyi, sorry. It is a name of bound. So it states the follows. So let's consider the local parallel code in d dimensions, d space dimensions. If you have a local Pauli Kansas. The transversal gate. So that three-dimensional space, it must lie within the edge of A. That's a motivation to define a Clifford-Hierarchy in this context. So there's a like for given some dimensionality of the logical operators, there's a upper bound, some bounds on the action.
Define what's topological power?
Yeah, I didn't. I need to. Yeah, well, like I don't try to define that precisely, but let me try to define what I mean by topological. So like here, this local means that so we have some let's say the code is defined on Euclidean space where we have a qubit is supported on some sites, and there's some notion of locality. It just saying that each stabilizer is some local. And so topological basically means some statement about the co-distance. Well, I need to define co-distance, but let me first frame the definition of the topological. So basically it says that the co-distance D. So co-distance is basically the size of the shortest logical operator which acts not trivially on the course. So this is some smallest some logical operator, smallest symmetry operator which acts not trivially on the space. And this topologicalness claims that this co-distance scales as infinite as you take a system size. So system size is a linear size of a Euclidean space. This topological condition states that there is some family of the cores where you can scale the system size, and as you take the system size to be large, the co-distance also goes to large infinite.
Co-distance is a number of these logical operators.
Co-distance is co-distance is is the size of smallest operators. So let me take, for instance, let me give you an example. If you have a toric code on a rectangle, like this, there is some logical line operators, like that, something like this. And then this guy is shorter, and the co-distance is defined as some size of the shortest logical operator in the bidirectional dimension.
Size means the number of.
Size means the number of the size of the number of
the size of the support.
which is size of the support. Yes, size of the support. Size means the let's okay. So in the case of the Pauli transversal group, this is particularly simple. So in this case, so any logical Pauli operators as a tensor product of the some Pauli operators. And then you can just count the number of the qubits which is contained in this cyclic expression. And this defines the shortest Pauli operator, shortest logical Pauli operator. Take a smallest logical Pauli operator and then count the number of qubits included, supported on this operator. That's a co-distance. For instance, if you have a 1, 2, 3 qubits in these lines, the co-distance is 10.
How can the distance go to infinity while it remain local?
Sorry, for a second.
I probably didn't understand that. You said local and topological?
Yeah, so
how do you take the distance to infinity and be local?
Stabilizer are local. Here is the size of logical operator.
Yeah, size of logical operator can go to infinity. You can just say that some linear size of the fold is L, and then in the case of torical, if you go to infinity, if the system size go to infinity, code distance also go to infinity. So this is a topological code.
Going back to this hierarchy, the hierarchy 1, we have the operators which are built out of 1 qubit gates. Hierarchy 2 can be built out of 2 qubit gates.
Yeah.
Is it true that hierarchy 3 can be built out of 3 qubit gates?
Yeah, practically yes. Practically yes. Well,
there's a theorem that K hierarchy is can be built out of at most K qubit gates.
Well, I'm not familiar with this kind of the statement about relating the Clifford hierarchy of the logical operations to the implementation of the some in terms of some local operators. But the relation is just about the Clifford hierarchy and dimensionality. There could be, I don't know. I don't know if there's some particular relation we can say about the relationship between the Clifford hierarchy of the logical operations and the hierarchy of the local operators. There's no relation. Yeah. But practically, yes, in some cases, in many cases, actually, if you want to implement the logical Clifford gate, we typically sometimes need local non-Clifford operators, but I'm not sure about the general relationship between them.
Last one. Yeah. What's the meaning for K equals 1? That's that bound, for example.
So if you have just a one-dimensional operator, if you have just a line operator, this says that the line operator must be Pauli operators in the local Pauli transversal code. Local topological Pauli transversal. Well, I give you some outline proof about this argument. Any other question?
So then supported k dimensions means it acts on a hyperplane within the d dimension?
Yeah, so there's some locus, k-dimensional locus, and there's if the logical operator is supported on some k-dimensional locus, you must implement this strict set. So in order to understand this part, I think it's inspiring to start with some what is happening in the world. The sketchbook. Pick it up. Polyphos. So polyphos can be defined in the generic dimension. Let's say we have a three-dimensional polyphos, and then we take a three-dimensional Euclidean space, and then we can define a stabilizer. It's a ZQK cell. It's some line ZQK cell. You can define this kind of thing in the generic dimensions. But so in this case, in this topological setup, there's some logical Pauli operators. Logical Pauli X operator is supported on some surface in the case of three-dimensional topological, and the logical Pauli Z operator is supported on the lines. So for instance, like if you want to consider D-dimensional pose, the logical Pauli X is supported on a D minus one dimension, and Z is supported on a So in this particular setup, we're going to show the Bravyi argument. And this kind of argument can be generalized to generic local logical pose. So yeah, in order to establish a Bravyi, like suppose that we consider suppose that we have some unknown operator in one dimension. So this is some unknown logical operator. Unknown logical operator.
So your surface is just made out of x's?
What do you mean?
What is the surface? You said it's x is the x-axis, not how
Well, this is a logical Pauli X.
x on all the leads.
Yeah, so in this case, like a logical X is extended in Y axis.
It's an X in the ground state of the topological.
Yeah, so like
Does it have it with z? With z?
yes, it's supported on dual lattice. So like so you have some sheet on the dual lattice, and then like the dual lattice.
Oh, yeah, these two actually.
Yeah,
Otherwise, you wouldn't have it.
Yeah, exactly. And then like it comes with these guys. Yeah. Yeah, so like let's say we have some unknown line operators. So right, and essentially the Bravyi he found is just for the dimensionality of the operators. So in this case, basically it can be derived by taking commutator between this unknown line operator and the logical Pauli operator. So basically take commutator between S and the logical Pauli. See. Or commutator between the S and the logical Pauli X. And since the topological is topological, we can kind of freely deform the shape of the logical X operators so that the dimensional intersection between this line operator and Z is, in this case, it's an intersection between the line and the line. So it can be at the most point in the case of two dimensions, but in higher dimensions, there's no intersection in general. So this commutator is trivial, actually. And in the case of the commutator between
Trivial or supported a single point?
In two dimensions, it can be supported on a single point. It's supported on a single point, but in higher dimensions, the intersection between line and line, it can be resolved.
Generically, but it could be that it's
Yeah, but since this is, since the code is topological, like you can kind of deform the shape of the logical operator without like changing the logical operations. So we can take some particular representative of the logical operators so that they doesn't have an intersection, and then like yeah, since this is topological, we deform that the commutator shouldn't change. So and in this case, where X is more extended operators, so it could have some point like intersections. But anyways, like these guys must be local operators. Therefore, but there's some assumption of the co-distance. Co-distance has to be large. In particular, which means that there is no point-like logical operators. So this local operator must act trivially on the co-space. So this has to be just a phase. So which means that the SC is like a C terminal. This is phase. this guy has to be a face. Therefore, this X actually has to be the Pauli operators. Okay. You can run this kind of a dimensionality argument. So, for instance,
If somehow your code doesn't have surface operator, then you can improve this bound.
sorry, what kind of setup do you want?
Well, if you don't have, let's say, logical operators supported in codimension one, so you don't have access.
Yeah, but well, the generic statement we can say, based on that assumption, is that you can always find the representative of the logical Pauli operators such that it's supported on a lower dimensional locus. So it has to be essentially lower than d-1 dimensions, well, equal or lower than d-1 dimensions.
Representative?
Well, like some deformation of the logical operators such that it doesn't change the logical actions. Yeah. So
How do you?
let me try to give how the generic argument works.
Can we have something like a three-loop grading? It's
Three-loop grading is
loop, but this is loop surface, but we could have loop.
three-loop grading is typically for the some non-Abelian topological order, signature of non-Abelian topological order. The Pauli stabilizers doesn't have this kind of thing. So
It violates the assumption of local topological stability.
My comment is that if you have a topological order with a three-loop grading, I think it has to be a non-Abelian topological order, and it cannot be realized by Pauli stabilizers.
It doesn't fit into this.
Yeah, I think so. Well, I'm not sure of what kind of the commutator or some algebra logical observable corresponds to the three-loop grading, but
Why this means S is Pauli?
because there are complete in generic Pauli stabilizer, logical Pauli stabilizers or toric code. There's some complete set of the logical Pauli operators. So I mean the logical qubit space is some bunch of qubits, and for each qubit there's some logical Pauli operators. And if for any logical Pauli operators, you can say that its commutator must be phase. Means that this space has to be Pauli operators. Yeah, this is clear. Yeah. Yeah, so let me try to say how the generic argument works. So in general, suppose that in general, since the code is Pauli stabilizer code, there's some complete set of the logical Pauli operators. A priori, we don't know the shape of these logical Pauli operators, so it could be really extended in spans over the form space, and that's what you are worried about, right? And then there's a so-called cleaning lemma, which is to say that suppose that we within the d-dimensional space, suppose that there's some ball region whose size, whose number of qubits within this support is smaller than the co-distance. So this is the size of the R, smaller than co-distance. In this case, there's a so-called cleaning lemma. Which claims that we can deform the Pauli operators without changing the logical action, such that a support on R is empty. Yeah. So we can establish using this topological condition. This is, I think, established by Bravyi. And basically, the logic goes for instance, in the case of the two-dimensional Pauli stabilizer code, we basically Bravyi paper separates yes, takes some mesoscopic triangulation state on the space, and then decompose the space like this. Then there's some triangular region which looks like a ball. And then we can use the cleaning lemma for this union of the balls such that the resulting logical operator supported this subscalar of the nearby this simplex, one simplex or several simplex. So that's how, this by using this cleaning lemma for generic given logical Pauli operators, we can bring its form into some lower dimensional support. So then we can use this kind of dimensionality argument to claim what we can define. Yeah, so that's a generic logic. So, but in this particular case of the, let me just work out the particular example of the tonic force. For instance, suppose that this S is a surface operator. Then because of this dimensionality argument, it's committed that between Pauli, logical Pauli operator and S can be the line operators. Then we say that the line operator has to be Pauli. And this is some other logical operators because commutator of the logical operator again defines the logical operators. So this is a logical operator which is supported on line and it has to be Pauli. And then we have said that because of the definition of the Clifford operators, this S has to be Clifford. And based on this inductive definition of the Clifford hierarchy, if you have a d-dimensional logical operator S, it has to be generate logical gate within the some Clifford hierarchy of K. Okay. So this is a generic argument. Based on what I said about the this generic topological code, this kind of dimensionality argument works for the generic topological powering local cylinder code. Okay. All right. So let me keep. So before going to the non-Clifford, Clifford stabilizer models, let me give you some famous example of non-Clifford gate in the Pauli stabilizers. This is kind of inspiring for defining the discussing a subclass of the verification part. So this is so this is the T2 cube toric code for T2 cube case theory. So equivalently, this is sometimes called the color code. This particular realization of this theory is called the color code, and it supports some transversal logical T gate. This has a logical T gate, and T is a diagonal. This is a non-Clifford operator, which is the genuine element of the hierarchy 3. And people like T gate because it's a single qubit logical non-Clifford. So it's kind of convenient to build the efficient universal case. But so you will define. So let me try to define some symmetry operator, logical operator of this 3 copies of toric code that generates a image. I think it's very interesting thing. So, so in order to define this kind of thing, so let me try to remember some generic symmetry of the case series, G2 case series. So this points us in the case of the G2 cube case theory. There are like three gauge fields, which I denote as the AR, LG, and AB, because it's a color code. Sometimes people label this C2 cube in terms of the color RGB. And in this kind of the case theory, there's some particular symmetry operator, which is very helpful for defining the non-Clifford operation, which is called gauge density. This is some topological operator of gauge theory. So if you have a G gauge theory in generic dimensions, let's say like a G gauge theory in D+1 dimensions, there's some topological operator which is favored by Foucault. What is the definition of this topological operator? It's basically just defined by inserting the topological response into some a codimensional K, the K-dimensional subspace of the whole spacetimes. For instance, in this case of the G2 case theory, G2 cube case theory, we can define some two-dimensional topological operator by the product of the AR AG. So this is an element of the H2 of the G2 cube. Q1. And in the condensed matter language, it is called understood as a response of the cluster state. But here, physically, it can be regarded as some decorating the cluster state with C2 times Z2 symmetry and then gauge the Z2 symmetry. Then it defines some defects of the topological order. And so by this kind of decoration of the SPT phase, you can define some symmetry operator, some logical operator of the sunrise cosine. And that's what it is.
It is not the part of the action of the theory, we just insert.
Well, so if you insert in the, for instance, in the case of the D2 square toric code, you can insert the cluster state and gauge, then it defines some symmetry defect.
Is this related to identities?
Yeah, so this is a symmetry defect, but if you kind of sweep the symmetry defect, you can kind of pump the symmetry defect by a finite circuit.
Yeah.
And by pumping, the symmetry action can be implemented by the finite circuit at the end of the day.
People also did this. The first mentioned three loop rating statistics. People did this for H3 and then A.
Yeah, so I think that you are talking about some diagram fit and twist, where the twist is defined in the whole space-time. Where this,
Precisely, but
I think that the sleep rebuilding is mostly about the twisted case theory. So in this case, its magnetic fluxes can become non-Abelian, and then around this insertion magnetic flux, the loop operators can also exhibit the non-rebuildings. And this is mostly about the non-Abelian, this twisted case theory. So in this case, I think you're mostly talking about the degree K equals to D+1. So in this case, its insertion is polar spacetime. So it just defines a twisted case theory. And you can understand this as some lower dimensional twist. So a twist which is only inserted in the lower dimensional locus. Then maybe you could discuss some three-loop braiding, which within the insertion.
Remember, this was discussed using Clifford-Hierarchy.
Oh, that's I don't know.
It's I think Benny Yoshida used Clifford-Hierarchy to discuss.
Benny. So this actually the perspective of the logical operators in terms of generalized symmetry was originally Benny's paper. So maybe he may be discussing in relation to three-loop braiding.
Why he used the
remember. But Okay, so this is a case video operators. And in order to define this T-gate on the QP theory, okay. It's a kind of actually the all is defined on the some specific geometry of tetrahedron. So like we have some board with a boundary. So we have some Z2 theory with a boundary. We need a boundary to define some Z action or T-gate. And let me try to explain how the boundary works in order to have interesting logical actions. So in the case of let's consider some Z theory in the bulk and there's some gap boundary. Suppose that there's gap boundary and gap boundary, let's say the gap boundary can be described by breaking the gauge group from G to K, like gauge show one. Then in the bulk, you have some symmetry operator, which is G covered by some group motion. And this is defined by some integral of the some topological response in the bulk. But typically you want to, in order to define the interesting logical action, we want to terminate this logical operator into the boundary so that it again defines a topological operator in the presence of boundaries. In order to do that, we need to find some boundary topological action. So like we consider some omega, a restriction of omega into the unbroken gauge group K. And in order to be able to find some boundary topological term, we need to be able to find some trivialization of the omega once you restrict to the gauge group K. And then, like, if you are able to find such a trivialization, we can define some bulk boundary logical operator, which is a integration of the bulk, integration of omega in the bulk. In addition to that, we also want to include boundary integral. This defines some bulk boundary topological action, but this is immensely helpful for defining some logical operator in the presence of boundaries. And actually, this is not the end of the story. In order to talk about the T-gate of the code, T-gate of the R code, actually we need also need some hinge. So you have some pair of the distinct gapped boundary, and this gapped boundary meets at some corner. And then in this case, like you have some pair of the boundary combination. The boundaries. So here we need to restrict to K, and here we need to restrict to K prime. And then we have some boundary combination with the logical operators. And then we also need to ensure that it defines a logical operator in the presence of the corners. So in the corner, the unbroken subgroup is some common take to be common unbroken subgroup of the K K prime. So in order to define the logical operator in the presence of a corner, then we need to ensure that if you restriction of the K minus eta minus eta prime at the unbroken group is again trivializing some kind. So then after adding the corner hinge, then it defines some bulk boundary corner logical operator. And with this insight, let me try to give you the definition of the T-gate presence of the in tetrahedron. So let me like to do the time. Let me just outline this out. So yeah, it's gonna be very good because I also wanted to talk about non-Pauli. So you have some 1, 2, 3 gauge group in the park. But here we break into the on each like a face, on each triangular face, we break in, the gauge group into some subgroup. On the bottom, we break into the diagonal. So yeah, so you have some in the bulk you have some 3 gauge fields, 3 zero gauge field, A1, A2, A3. And then on each boundary, there is some certain boundary condition on the gauge fields. In here, like A2 equals 0. Here A1 equals 0. And in here A3 equals 0. And then like on the bottom, the gauge, because of this diagonal pattern breaking, pattern of breaking is boundary condition of the gauge field is like this. Okay. And then, based on these boundary conditions, the logical operator is defined as the integration of this couple of Z2 cube SPT action in the bulk. And this due to the story I have outlined in general, this action might not be like vanishing in other boundaries, right? But in the most of boundary, just vanishing. Like for instance, in here, A1 equals 0, so therefore this guy is also vanishing. But on the bottom of the boundary, because of this diagonal symmetry breaking, basically it's not vanishing as a cochain. So like on the bottom, it is turned into the A1 cup A1 plus A2. But this is actually co-boundary, so you can rewrite this guy into the taking C4 if static co. So you can find a boundary trivialization, and further you can also find some hinge trivialization. So here, there's some additional which is really the so at the end of the day, the action of the logical operator on this T is given by this. You integrate the arc A1, S3, A2, and the also boundary contribution. Bottom boundary, which is over A1. Also, there's some spawner, one spawner, which is sorry. So here one can see that by taking the trivialization of the restricted cochain, we need to take some 1/2. If you want to take a trivialization of this cochain, we need to take 1/2. And that's how we get some logical S action, some Z4 operation, Z4 logical operation. And further, once you restrict it to the corner, you get the 1/4, this Z8 action of the logical field. So the presence of the boundary of corner is really important in this story to get the logical T-gate. And you can, once you have this kind of expression, this is some symmetry operator of the Z2 gauge theory, and there's a corresponding finite circuit which can implement it. So therefore, this is a transversal logical gate. So yeah, sorry for the excess in the time, and in the remaining few minutes, I want to just very briefly explain how you can surpass the Bravyi by going to the non-Pauli circles. So let me just explain one particular example how where this kind of surface of the response. So we use a twisted case theory. So So this is a non-Abelian topological order where the twist is defined by the A1 out. So this is a twisted T2Q case theory, which is equivalent to the hydral proof theory. And this theory admits the realization in terms of some stabilizer code, but this is not a Pauli stabilizer code. It is a Clifford stabilizer code where each stabilizer is a sub-Clifford operator. And now it doesn't commute with each other. It just commutes within some, it just doesn't commute with each other, but it has a common ground state. So it's more like frustration pre-Hamiltonian. And actually looks like can be defined as square-root. It can be. It looks like some Pauli X operator for toric code on top of the decoration the control C. And we can see that this defines Clifford stabilizers. Then, so let me. If you go to this kind of the twisted case theory, it is very helpful to think about some automorphism of the gauge group. So in the gauge theory, there's a symmetry. In addition to the gauge tensivity defect, there's always some zero-form symmetry, which implements automorphism of gauge groups. So like autophagy, like charge conjugation of U1 gauge theory. And typically in the untwisted case theory, it just has a very boring action because it just swaps the logical qubits. But in the case of a twisted case theory, automorphism symmetry becomes much more interesting. This is because, like, let's say that some diagonal Witten twist is omega, and then this let's say the automorphism is a G to G, and then like this omega is mapped to some omega, this probable omega by automorphism, and then so this mapped guy is equivalent to omega as a sum for chain. Sorry, it's a cohomology, but this automorphism can put in principle shift omega by some boundary. And then so in this case, like you can't simply define the automorphism operator in terms of some transversal swap or this kind of the trivial on-site operator which swaps a qubit. But in addition to that, we also need some additional electric operator, additional gauge density type operator to define topological operator in swap. So the topological operator looks like this. So there is some operator which implements automorphism of the gauge theory. So this guy just maps, this operator just maps like a gauge group, element of the gauge group according to the automorphism. And then like this doesn't alone define the topological operator because it changes the topological action. So in addition to that, we also need to decorate some like this automorphism operator with some additional gauge density type operator. And this is very important in order to define some. And this can have some very rich action in the gauge theory. And it actually gives rise to the interesting algebraic structure of symmetry in the gauge theory.
So why does it change action? It changes omega itself.
It changes omega itself, but it changes the cohomology plus omega itself.
Does not change. Doesn't that mean action does not change that?
No. But in order to claim so like So in order to qualify as a,
So the partition
Yeah.
probably has not changed, but actually.
in order to qualify as some topological operator, we need to make sure that the partition function in the presence of the symmetry defect doesn't change under the deformation of the operators.
Is this
Yeah.
like time reversal at theta equals pi? The action is
Exactly.
not invariant, but theta pi and minus pi and pi are equivalent.
Yeah, exactly. So like
That's why saying, okay, yeah, understand exactly.
yeah, exactly. So in this case, the time reversal defect has to be decorated with some chance time abstraction. Yeah, it's similar to that. When the topological action is not invariant at the level of the chance, we need to redefine it. So this kind of technique has been appearing in many contexts, especially in the context of the non-invertible symmetries. Recently. So
But this is invertible.
yeah, this is invertible, yes. Yeah, if you find the All right. So this kind of so the thing is that so in the context of just a quantum code, we can find some automorphism symmetry, which is interesting enough to investigate. So in the twist, A1 up A2 up A3, let's consider the automorphism. It shifts the A2 to A1 plus A2 plus A3 and leaves other thing. So this is automorphism. This can be qualified as a symmetry of the DFK theory because this changes the cohomology class of twist invariant. So if you consider the A1 comes to A2 comes to A3, shifting a gauge group like this, the cohomology class doesn't change, but they can be shifted by the chance. A1, 3. So this shift is invariant in the different T. So then the T gate can be defined on a triangle. So you have a T2 gate theory, T2 cubic gate theory, and then we have some actual boundary condition, like A equals 0, A2 equals 0. Yeah. And then we have some A3 equals A2 equals 0. So this the topology I want to consider some triangle with some 3 boundary conditions. And then we define this automorphic symmetry in the presence of this gap boundary. And at the end of the day, you can check that this defines a T-gate. So it looks like there's some operator which implements automorphism. And in addition to that, there's some, because of the story I have said earlier here, we need to enrich this action by some boundary guy, integration of the boundary guy. This is the park. And then then there's some similar story to the T-gate in the color code. So we further need, in the presence of the boundaries, we further need to extend the definition of topological operator in the presence of a boundary so that this integration again defines a topological operator in the presence of the boundaries. And then it turns out that we further need to add some boundary operator, something like this, in order to define the whole logical operator. And this you can find a 1/4, and this turns out to generate some logical key action. And this code indeed support the single logical qubit. So takeaway is that if you go to the Clifford transversal code that realizes a twisted case theory, you can actually surpass the Bravyi König bound and realize a single qubit logical T-gate. And you can generalize this kind of thing to the higher dimensions, for example. Like in higher dimensions, we can find a family of Clifford-Hierarchy stabilizer code, where each stabilizer is within Clifford-Hierarchy, such that it has a single logical qubit and has some non-Clifford operators with a higher hierarchy. And also, the final comment is that there is also interesting paper by Sakura's group, which basically shows that by considering the Clifford hierarchy stabilizer code on a triangle, we can find the rest of the codes with a single logical qubit and generates arbitrary hierarchy. Okay. So yeah, so you can completely collapse the Bravyi König bound if you go to the non-Pauli course. Okay, so that's what I want to say today. So yeah, thanks for listening.
Any questions for me? Maybe mention that. Could you repeat this? What is the statement about universality of gates if you include this T gate?
Well, so actually, the only transversal gate of this code can't really do the universal computation. That's very general for the topological code. That's a very general program of topological code. So if you really want to do the universal computation on using this, like typically people do some switching, so-called code switching. So because this code alone cannot do like a full Pauli or Clifford operators. So we want to invest on the surface code on which we can do the Pauli or Clifford. So
there is a statement that this T gate code plus conventional Clifford gates is not enough to generate everything.
It's enough for universality. Clifford plus T is universal.
Clifford plus T is universal?
Yeah. So basically, in the more practical context, we start with some surface code, and by the stabilizer measurement, we switch to this Clifford stabilizer code on which we do the T gate. So within this scheme within the surface code, we do the Clifford, and then by this switching of the codes, we do the non-Clifford gate and switch back, and then it's universal surface code.
It's time for
Yeah, thanks.